Hello, everybody. Welcome back. So at this point, hopefully you've gone through and are getting familiar with the anatomy of the kidney. The first video is taking a look at the blood supply to the kidney. So now we're going to take a look at the first processes of renal physiology. I'm going to do a little overview slide, which we'll see on all of the mini lessons for the physiology sections. And then we're going to focus specifically on what happens at the glomerulus, which is filtration. So here is an overview of the nephron anatomy with some of the processes that will be happening. So again, at this point, you should be pretty familiar with what a nephron is, the different types of nephrons, and they're kind of the path of which this filtrate is going to run through. So the nephron begins at the glomerulus. So when we take a look at that structure here, it's kind of this area right here. So this includes the blood coming into the capillary through the afferent arteriole. Filtration happens in the glomerular capillaries, drained by the efferent arteriole. And then you have the renal corpuscle, which is your the glomerular capsule of the simple squamous epithelium surrounding the capillary beds with the podocytes stuck to the surface there. So this is the first place we're going to be doing some physiology with the filtration that happens in the glomerulus. We are then going to take a look at the proximal convoluted tubule. Again, proximal means close to the beginning. So we'll take a look at the physiology and what happens in the proximal convoluted tubule. We will then move on as the filtrate moves on through this path to the nephron loop, sometimes called the loop of Henle. There's a descending and an ascending limb, so it goes down and then comes right back up. And then that filtrate moves into the distal convoluted tubule, or DCT. And then we'll talk about the physiology that happens there. And then all of the nephrons drain into the collecting ducts, which will lead to the papillary ducts, which will lead to the minor calyx, which is that collecting structure at the tips of each of the pyramids. So this is our path. So we're going to do, first we'll talk about filtration, then we'll talk about the proximal convoluted tubule, the loop of Henle, the distal convoluted tubule, and the collecting duct and papillary duct. We don't do too much about the papillary duct. So we kind of end our journey in the collecting duct. So this is the path of what we're going to be doing, and we're going to start with the glomerulus. Okay, so here's that picture, kind of this diagram up here that we saw in the first mini lesson with a close-up of those capillaries, with the afferent arteriole bringing blood into the glomerulus and the efferent draining from the glomerulus. One thing I forgot to mention in that first lesson, which I will here, is I wanted to, it's in the notes, but this little structure area right here is called the juxtaglomerular apparatus, or sometimes called complex, the JGA. So the juxtaglomerular apparatus is a collection of smooth muscle of this in and out of the arterioles and some of those simple cuboidal cells of the distal convoluted tubule. This is the place where, if you remember from our endocrine, this is where renin and erythropoietin come from. So if you remember EPO, which is a hormone which increases red blood cell production, and renin, which triggers the whole renin-angiotensin mechanism of increasing blood volume and blood pressure, that is the location of where the hormone and the enzyme comes from. So kind of a cool reconnect to what we talked about in the endocrine system, seeing the actual physical location of where those hormones come from, or the renin is an enzyme and EPO is the hormone. But it makes sense because if we are monitoring blood volume or oxygen carrying capability, that we have these receptor cells, these monitoring cells right there in the efferent and afferent kind of junction with the distal convoluted tubule, so we can monitor blood volume and blood pressure, we can monitor fluid balance, and we can monitor oxygenation, so if we need more red blood cells, if we're anemic. So the JGA is a very important structure in this kind of glomerular apparatus, the glomerulus and the DCT. So I just wanted to point that out. I forgot to mention that last time. Okay, so now let's say we have blood coming into our afferent arteriole, going through the capillary bed and being drained by our efferent arteriole. So first of all, before we get into all this numbers and a little bit of math, we have to appreciate the uniqueness of that setup. So if you remember, a general capillary bed is blood goes in via the arterial side. We have the capillary bed, and then is drained at the venule side. So that takes us all the way back to 232 in our capillary exchange lesson. We're talking about filtration and reabsorption on the venule end. Because we are draining our glomerulus with an arterial, arterioles have that smooth muscle tunica media, and they're not wide open like a venule would be. So the pressure inside the capillary bed can actually reach pretty high. And so if you remember, our capillary hydrostatic pressure in a regular capillary bed went from 35 to 18, right? So it started at 35 millimeters of mercury. The arterial end, it dropped down to 18 millimeters of mercury as it drained into the venule end. And that's where we had the net filtration out and then the net reabsorption back in. By the time you had that, the blood colloid osmotic pressure kind of stayed steady state 25 all the way throughout. So you can go back and review, I think it's chapter 21. So this is a typical blood pressure, capillary hydrostatic pressure in your peripheral capillaries. But now if we're going to take a look at the glomerulus, it is not a typical blood capillary. It's got that efferent arteriole, which is more resistant. So we're going to expect the pressure inside the glomerular capillaries to be a lot higher, and it is. So if we take a look, this is, I'll highlight it here, if I can get my colors right. So the glomerular hydrostatic pressure, it's called the GHP. Okay, so I'm gonna do a little bit of math calculations over here. So we're gonna start, it's averaging around 50 millimeters of mercury. So it's gonna be a little bit plus or minus. So we'll just go with the averages to make the math work. And so this is a typical pressure of an outward force. So the glomerular hydrostatic pressure is basically the blood pressure of the capillary, and it's pushing things out of the glomerular capillaries. Okay, now we have to take a look at some of the things that might oppose that. So just like we had blood colloid osmotic pressure in our peripheral capillaries, we have the same thing here, right? So our BCOP. So blood colloid osmotic pressure is still true because we have those large plasma proteins and all of the albumins and the things that are inside the capillary that don't get filtered out, and they have that osmotic draw to push things back in. Let's get the right color here. So that is 25 back in. So that's an inward, it's an opposing force. So that's kind of, you can see that 25 there. So if we were to have a net filtration pressure, or sorry, a net hydrostatic pressure, it's about 25 out. So we cancel about half of that capillary hydrostatic pressure with the blood colloid osmotic pressure. Now we have a new pressure that we have to identify. It's called the capsular hydrostatic pressure, or CSHP. This is the idea that your nephrons, the Bowman's capsule, or the glomerular capsule, and the PCT, and everything else down the line is filled with fluid. It's a hydrostatic environment. So if you are trying to push fluid against a fluid-filled tube, it's going to resist that push. And so this is a smaller little inward flow of about 15 millimeters of mercury. That's a little orange arrow there. And so this capsular hydrostatic pressure resists the outward flow. So we'll do another little subtraction here. Get my symbols. And so we have a net filtration pressure of 10 millimeters of mercury out of the glomerulus. So that's what we, nope, I don't want a black highlight. How about yellow? This is the same thing here. So if we start with a capsular hydrostatic pressure of 50, subtract blood colloid osmotic pressure and subtract capsular hydrostatic pressure, both just being opposing forces, opposite directionality of this flow of fluid, we would end up with a net filtration pressure of 10, pushing things out of that filtration membrane. Now, if we take a look at what that filtration membrane is, remember it is our fenestrated endothelium, so that's kind of our pores right here. And we have those interlocking pedicels. These are little finger-like projections on the podocytes. We have things that will push out through the pores and through these filtration slits. If they are small enough to fit, this 10 pressure will push that stuff out into the glomerular capsule that will be picked up and then ferried on down the rest of the nephron, the PCT, the loop of Henle, the DCT. Okay, so this is the first part of renal physiology, is the actual filtration that's happening at the glomerulus. Now, if we take a look at these numbers, it is all driven by capsular hydrostatic pressure, that 50 starting pressure that is basically determined by your overall systemic blood pressure. So let's say you have low blood pressure. So for whatever reason, you have low blood pressure. Maybe let's say instead of an average of 50, you average 40 out. So you have an overall systemic loss in blood pressure. Your blood collage osmotic pressure is not going to be any less because that's just the nature of albumins. You know, low blood pressure does not necessarily mean you're going to have less albumin. And so if we subtract this, what's 45 minus 25? We have 15, right? And then, so that would be our net hydrostatic pressure. And then we have this capsular hydrostatic pressure that is going to be opposing that capsular hydrostatic pressure. And again, that capsular hydrostatic pressure is not going to change. Your nephrons aren't ever going to be empty. And so what we end up with, 15 minus 15, is 0. So if you have an overall drop in blood pressure by a factor of 10 or units at 10 units, if we start with an average of 50 and our blood pressure goes down to say about 40 in the glomerular capillaries, are your kidneys working? No. If you have 0 filtration, you're not filtering your blood. So you have 0 output and your kidneys basically have stopped. Now, we don't typically see that very often because we have a very strong regulation of this process. And we're going to see that on the next slide, is regulating the GFR, which stands for Glomerular Filtration Rate. Okay, my PowerPoint just stopped in the middle, so I had to start on just this slide over again. Hopefully it will track good enough. All right, so we just got done taking a look at the filtration of the glomerulus. So there is a value that we need to maintain for homeostasis called the GFR, glomerular filtration rate. And the average or normal glomerular filtration rate is about 125 mils per minute. So in about a minute of time, a glomerulus can filter out 125 mils, or your kidneys can filter 125 mils per minute. Is the rate. This is our goal. This is to maintain homeostasis. Now, in the last slide on that example, if overall blood pressure drops and we bring that net filtration pressure to 0, our kidneys are not functioning. Our GFR would be 0. We're out of homeostasis. So we need some ways to kind of built-in ways to maintain filtration. Otherwise, we'd be circulating, toxic blood around without a way to get rid of all of those waste products. So there's 2 major ways that our kidney maintains homeostasis, maintaining that 125 millimeters per minute. We have autoregulation and hormonal regulation. So in the autoregulation, let's say we're at homeostasis in that little purple circle, normal glomerular filtration rate. And for whatever reason, blood pressure drops and the GFR goes down. So let's see if we can fix the problem just locally. So if you remember, the glomerulus is fed by an arteriole and drained by an arteriole. That's a unique physical situation. So it's like we have 2 muscular doors, in, that's the afferent, and an out, that's the efferent. So if we want to increase the blood pressure within the glomerulus, we want to open up the front door, allowing a lot more blood to come in, and squeeze down and close on the back door to prevent blood from leaving as easily. And both of those things are going to increase the resistance, increasing pressure within the glomerulus. So we see that here. We are going to dilate the afferent, that lets more blood in, and we can constrict the efferent, that's the out path. If we close that down, we're increasing the pressure within the glomerulus. And then also they show here in this diagram the contraction of the mesangial cells. These are little cells that are kind of helping to support the capillaries, and they can constrict in almost like a little vasoconstriction of the capillary. So opening up the afferent, closing down the efferent, squeezing a little bit with the glomerular capillaries themselves, all are going to increase that glomerular blood pressure. And that will help us increase our GFR to get us back up to that net 10 filtration pressure, because that's going to maintain our 125 mils per minute. And if we're good, if we can kind of keep this, the afferent open and the efferent constricted, that's going to help maintain a GFR. If that's not enough, right, autoregulation, we try to do the local control first. If that's not enough, we can go up here into this path and try to trigger system-wide increase in blood pressure. Because if we don't have system-wide increase in blood pressure, the autoregulation is only going to work for so long, and we can't completely shut down the efferent arterial, otherwise that is just not possible. So if you remember, that juxtaglomerular apparatus is going to recognize this drop in blood pressure that cannot be maintained with autoregulation. So it's going to trigger renin. So if you remember the whole renin angiotensin mechanism, I'm not going to go through all the details here. You can go back and review it in the endocrine chapter. You can go back and review it in the blood pressure regulation chapter 21, I believe, but it's all the same thing. So renin triggers the conversion of angiotensinogen into angiotensin 1. The ACE in your lungs converts that to angiotensin 2. And so here we have angiotensin 2 triggering all of these things, right? So angiotensin 2 triggers aldosterone and ADH and your neural responses of widespread systemic vasoconstriction, increased consumption of water, increased blood volume, increased blood pressure, increased glomerular filtration rate back to homeostasis. So there's a huge network of signals that are going on to try to maintain GFR. It's that important to have all of these things set in place so your kidneys can keep filtering out what they need to filter out. Okay. In this process, we're like, okay, so this is our first step of renal physiology. We got to filter the blood. But what comes out of that? Filtrate. Well, anything that's small enough to fit through those filtration slits, the pores of the fenestrated capillaries that can get pushed out by that net filtration pressure of 10. I like to say it's good stuff and it's bad stuff. Everything comes out that can go out. Now, blood cells stay in, proteins stay in. Anything larger than the filtration slits, which I want to say like 5 to 9 nanometers, you don't need to know the measurement of that. But it's not like we're drying out the blood. Because we still have blood, it's fluidy, the blood will be leaving via the efferent arterial, but it's going to be a lot different in composition. It's going to be missing all of the stuff that got filtered out, good stuff and bad stuff. Now, as we move on to the rest of the nephron, it's the job of the PCT, the nephron loop, the DCT, and the collecting duct to reclaim the good stuff and put it back into the blood and let the bad stuff get peed out. That's the whole goal, is to make urine, which is getting rid of these organic wastes that got filtered out at the glomerulus, but along the way, we're going to start reclaiming some of the good stuff. There's a statistic that I usually mention when we talk about the GFR and filtration, is that your kidneys, your two little kidneys about this big that sit on your back, like right behind your ribs, they filter about 180 liters per day, which is about 50 gallons for us English non-metric people. So how much do we urinate a day? Nowhere near 180 liters, nowhere near. Our average urine output is like 1.2 liters. So our glomerulus filter out 180 liters of fluid, right? That's collected in that Bowman's capsule, in that glomerular capsule. But by the time it comes out of our bodies, it's only a little over 1 liter. So where does all of that fluid go? It gets reclaimed by the rest of the nephron. It's beautiful. Renal physiology is just so amazing. So we filter our blood every 4 to 5 minutes, our entire blood volume. We make this huge amount of filtrate, but it's the job of all those microscopic little tubes of nephrons to reclaim mainly water, but it reclaims any of the good stuff that got filtered out because glucose is small enough to filter out, sodium, potassium, amino acids, vitamins, other organic nutrients, those things that get pushed out, we don't want to just pee those out. We can still use those. So it's the job of the nephron to reclaim the good stuff, let the bad stuff stay in, and that's what is our will make our urine. So these next few videos are going to be breaking down exactly what's happening in each of those parts of the nephron, the PCT, the nephron loop, the DCT, and the collecting duct, to get us to the end point of the waste product while we reclaim all of the good stuff, with some bonus of helping to regulate blood pH and fluid balance. Okay, so that wraps up our filtration lesson. I will see you next time at the PCT. Bye.